Hello everyone, here's Bernardo Souza from FACCTs. I'm happy to be here at the ORCA 6 release event, and today I'm going to present you some of the new ORCA 6 optimizers. And those are Goat for conformational search, Docker for intermolecular interactions, and the DeltaSCF for excited states. Hope you can have fun with it. First of all, let's talk about Goat. Goat is a global optimizer algorithm, and the name is related to the animal and nothing to sports. I just heard about that after the fact. I didn't know about any of that, just to make it clear. It's an algorithm to find the global energy minimum, so the lowest energy conformer, and the ensemble around it. So let's start about discussion with what is a conformer and what is not a conformer. So you can see from the red ball that you see on the plot here that this is not a minimum. This is just a structure on the potential energy surface. The blue ball shows a minimum, and the green ball shows the global minimum. So you might have several possibilities for a given potential energy surface, as you know. But let's think a little bit about it. Take, for example, the histidine molecule. It's a very simple amino acid, rather trivial, 20 atoms. How many conformers would you guess exist below the window of 3 kcal per mole? Well, that's actually 20 conformers. It's more than 20 conformers, which is quite a few for such a small molecule, right? You can see the conformers here. The global energy, the global minimum is here on the XTB potential energy surface, and you have another one at 0.5, 0.9, and 1. They all look more or less the same, and it's hard to figure out what is what, right? You could say, yeah, that's not too difficult. I could have figured out that by myself. Well, that might be true. Let's take a different system. So let's take oseltamivir, which is an antiviral drug, an important one. 50 atoms. There's a ring. It doesn't seem to be too flexible. How many conformers would you guess there are below this 3 kcal energy range? Well, there are 450, more than 450 on the XTB potential energy surface at least. And as you can see, the global minimum corresponds actually to only 2% of the whole Boltzmann weight, because there are so many conformers that the weight is distributed all over them. And basically the difference between that and the higher one at 6, it's almost nothing. You can barely distinguish between them, right? But the one at 6, it practically doesn't exist, and it doesn't contribute to anything that you would measure in practice. So knowing the global energy conformer and knowing the ensemble are key things in modern chemistry for flexible molecules. So let's take histidine again. Suppose you have 3 rotable bonds, and assuming 4 possible positions for each dihedral, that gives us 4 to the power of 3 possibilities, which is 64 conformers. Now, I said we have a little bit more than 20, but that's on the small energy range. Overall, you have more or less about that amount. In general, for n rotable bonds and p possible permutations, we have something like p to the power of n possible conformers. For oseltamivir, that would already be 260,000 possible conformers. For molecules that are a bit larger, like vancomycin, you would have 200 million conformers. And for something as simple as an alanine 10, which is just a decapeptide, not too special, if you count that it has like 28 more or less rotatable bonds, that's 10 to the power of 16. Which means even if you had a method that could calculate each conformer in 1 microsecond, you would need years to calculate all that. So that's a very complicated problem. Pn implies that this is an NP type of problem, like an exponential scaling problem. Protein folding is proven to be NP hard, and I think it's easy to extrapolate that molecules also are. And that's a mathematician's way of saying, believe me, it is really hard. It's a complicated problem, and it's very hard to tackle. I just want to mention some algorithms from the literature. The popular modern one, it's called Bayesian hopping from Wales and Doyle. And the idea was to try to split the potential energy surface into bins and use Monte Carlo kind of kinetics sort of, or approximation to jump between bins. And they did that for only Lennard-Jones clusters because that's what you could do with a cheap potential at the time. There's also MD-based methods. Then later, Stefan Gödecke improved on that by doing MD and using MD to escape some barriers. And there's also some more stochastic algorithms like the ETKDG, which is actually an RGKit from the group of Serena, Reniker, which is a super also smart algorithm. You create a random distance matrix, and then you based on some topology rules, you can convert from the distance matrix into an actual 3D structure. But then I have to mention here the paper by Stefan Grimme and his group, which is CREST, where the idea is that you can start from some point on the potential energy surface and then start applying a bias potential that takes your molecule out of that region, like the green region here, which gets where you apply more and more bias potential until the molecule can go to new regions. In a way, it's an extension of what Stefan Götteke did, but with meta potentials. How GOAT works. So GOAT is, we try to learn from all that we saw in the literature, and we try to have something which would not depend on metadynamics or dynamics in general, because that requires millions of gradients, and that's not suitable for DFT. So, or higher level methods. So the idea of GOAT is just really to walk on the potential energy surface. You start somewhere, like the darker blue ball there. Then you take a random direction, you go uphill, downhill, as you walk on the potential energy surface, you collect everything that was found along the way and you move forward. So here's just a simple scheme of the algorithm. You start somewhere on the upper red ball there, you make some step, you reflect the gradient away from the minimum to walk on that direction. You stop once you perceive you cross the barrier, and you do regular optimizations and you check probability. So there's also temperature criteria, and you have multiple workers that are spawned with different temperatures, and they can be all parallelized and do the job for you. Cool thing is it can combine with any method from ORCA. So you can do that with DFT, excited states, DeltaSCF, anything. Of course, if you use DFT, it will be much slower, but still you can do it, which for metadynamics would be basically impossible, right? So here's one example of an alanine 10, and here it's an XTB potential energy surface, and I'm just showing how it folds into some kind of alpha helix. This seems to be very simple, but it's actually a very complicated example. If you ever tried something like that, you know what I'm talking about. This is super hard, and the fact that GOAT does it and CREST also does it, it's really cool. Here's one example of one drug approved by the FDA last year. It's a microcycle. It's a very complicated problem. Although it looks simple, it's actually hard. And GOAT finds the same global minima on the XTB surface as CREST. But as you can see, RGKit fails even if you add number of atoms squared, if you create number of atom square structures and then optimize all of them. And Confab, which is just a trial and error algorithm from OpenBabel, you can just randomly rotate angles. It also finds only higher energy structures, which is coherent with what I just said. The conformational space is just very, very large, and by trial and error it's hard to get there. Another example is a peptide, also a drug from last year. GOAT finds a certain global minimum, and from what I tried at least, CREST finds only something which is 6 kcal higher, which is basically wouldn't even exist on that potential energy surface. And for RGKit we generated 23,000 structures, and we only found something that was 15 kcal higher, which is completely inexistent then in this case. So GOAT works really well. Cool thing is that since it does not rely on dynamics and it just walks on the potential energy surface, it's easier to deal with clusters. So here's one example of GOAT clusters. It could be anything. I just picked this GOAT clusters, and you can see my initial structure is a flat surface of GOAT, 20 GOAT atoms on the bottom, and then it turns into this nice pyramid, showing that you can go very far away from your starting point, even if the topology is completely free, which adds a lot of new degrees of freedom, right? And it really works. Also, it's important for reactions, because most people think that a reaction occurs as the black line shows here, but actually a reaction is an ensemble of reactants that can turn into an ensemble of transition states and products, and finding the lowest energy ensemble for a transition state is a key thing, and it's very popular in the literature right now, and ORCA can do it. So here I'm showing one example of a reaction. I just took some this outer reaction. I found the transition state from the NEBTS, and I ran a conformational search on the transition state by constraining the reaction coordinates using R2scan3C. And you can find from a random initial molecule that I tried, you find some TS that's 6 kcal more stable than what I tried, which is a factor of 25,000 on the reaction energy. So there's much more about GOAT. I would like to talk more about that. We can ask questions next. There's a lot more you can do. It's all there on the manual. Now, switching to a different kind of problem, the Docker. So now the objective here is not to find the global minimum of a single structure, but a collection sort of structures. Let's say you have uracil, what's on the right, and water. What will be the best binding mode between both? How would water best bind to uracil? That's the question we were trying to answer here. And the way we do this is by using swarm intelligence or swarm intelligence approach. Swarm intelligence are algorithms that are inspired by collective animals like bees and ants. And they're actually global optimization algorithms as well. On the right here, you can see how the collection of bees fight to find the global minimum, and they find it. And it's a really cool algorithm where you have a inertial component, so bees moving where they were moving before. There's an individual behavior, so each bee tries to find the nearest, nicest flower. And there's a social behavior, where each bee talks to the others and say, hey, there's a nice flower here, come check it out. For this particular application, we don't need a global optimizer, but rather we would need a algorithm that finds multiple local minima. So we instead took the swarm intelligence and we make it drunk and short-sighted and a bit dumb. And what you see on the right here is it's the actual algorithm already running. So you have this biphenyl with an alcohol group on one side and an amide group on the other side. And the gray balls are water molecules with a certain angle that I'm not showing here. And you can see that you start from a certain distribution of waters, distribution of possible solutions. And you can clearly see how they converge to these two local minima on the right and the left. So the general strategy here is you start from a decent, well-separated initial set of solutions. You use swarm intelligence to find multiple local minima. So it's a short-sighted, drunk swarm intelligence. And then you take a few of these, somehow filter them to remove duplicates, and then optimize all of them. It's very easy to use. Here's one example. If you want to create this pair, you would have your uracil as a regular ORCA input, and you just create a block Docker guest and give a file which would contain the XYZ of the water. And that's the result what you get with a certain interaction energy. Here is water with uracil, and then on the right is uracil with uracil, and you can do whatever you want. Of course, we don't only print the best solution, we also print many solutions, because number 6 might be the most stable on the XTV level, but number 9 could be the more stable if you do double hybrid DFT, right? So we print several solutions, and you can refine later using any higher level method. Here's also another 2 base pairs, just to show that you can have, it finds both pi stacking solutions and just hydrogen bonding solutions and all that. And here's one example of a beta cyclodextrin with some alcohol in the middle, just to show that it goes inside cavities. Even if you had a completely closed cavity, the algorithm will try to dock things inside the cavity. What is also cool is that you can have, if you have a file with multiple guests, it can dock all of them. You will see how does that work on the manual. And let's say you have a file with 3 water molecules, and you can add the first water, second water, and third water. Just to make clear, this is a rigid docking algorithm. It's important for those out there who know about docking, which means it does not try to find conformers at the same time it tries to dock. But you can use GOAT from the previous slides. You can take the result of that, the ensemble file, and you can give as a guest the ensemble file. So you would have all conformers from one molecule, and you can dock that on a certain host. Again, there's a lot more to say about that, but everything else is in the ORCA manual. I won't have time to explain much more about it right now. And last but not least, I want to talk about the DeltaSCF. DeltaSCF is an algorithm where we start, so we try to optimize to excited states of single determinant wave functions. So this was done also in collaboration with Jorik from the group of Professor Hannes Jonsson from Iceland. And the idea is more or less what I'm showing here. You have some reference state on the left, and you can define some arbitrary configuration, again, single determinant, but arbitrary configuration on the right, and you get some new variational state. You can call it an excited state. We have 2 methods in ORCA. One of them is the maximum overlap method, which is by Peter Gill, and the other is the projected maximum overlap method, so PMOM, which is by Randratjen. So I've implemented both of them, and you can use whatever you want. Also, the I1 can also, IMOM and IPMOM can also be used. It's very easy to define these states. You just have to take, let's say, formaldehyde, and then you take PBE, basis set, and DeltaSCF, UHF, and you define a configuration. So alpha conf 01 means you're doing some homo-lumo excitation on the alpha channel. There's more about that on the manual. You can, in principle, create arbitrary configurations using this kind of scheme. And here are some really cool results. So for double excitations, you can see here that the DeltaSCF gives results very close to CC3 and almost as good as the theoretical best estimates. And here we're using omega B97M V, which means it has even VV10, so density dependent correction. You can do everything self-consistent with a large basis, and the errors here are EV. You can also do core ionized states, so you can kick electrons from the core and it still converges to the SCF of that state, and do whatever you want on top of that. So you just say ionized alpha or ionized beta and the number of the core orbital, and you can kick that electron out. And here you see the results for the ionization energy of these molecules, and the bold letters there are the atoms from which the 1s electron was kicked out. It's also really cool for diabatic couplings. I'm not explaining too much, but if you know about Markov theory, you know that everything on that equation is relatively easy to compute, except for the HAB there, which is the diabatic coupling. But you actually can compute that with DeltaSCF if you use something called the generalized Mulliken-Hush theory. And let's take as an example here on the left, you have two ethylene molecules. One of them is a cation, the other is neutral, and you want to calculate the electron transfer rate between them. You can do that with the simple excitation on the DeltaSCF, and the results you get are actually as good as MRCI plus Q. I'm using omega B97MV again, and the results are in milli EV, so these are relatively small numbers. And as you can see, the DeltaSCF performs very well with distance, as good as MRCI plus Q or NFPD2, better than CC2, and much better than TDDFT. Another example for a benzene dimer, again, very close to MRCI plus Q, surprisingly close to be honest. But we're talking about ORCA, which means you can go really large, and you can take like polymers or these photovoltaics and stuff, and you can try also, and you can get, here I don't have the MRCI plus Q because it's just too large, but you have this NevPD2 results, and the DeltaSCF gets you almost there at the cost of a ground state calculation. Another interesting example, there's this benchmark for singlet, triplet, so excited singlet to excited triplet gaps, energy gaps, by Jan Mives and Stefan Grimme. As you can see, it's a relatively diverse set of molecules, and it's really interesting that we get such good results. So the black line is the experiment, the gray is the kind of the error bar, and you can look at the green here. The green is what you get from the DeltaSCF. So this is a diverse set of different molecules, and you still get really good results on these singlet triplet band gaps. Here I'm just showing that we also implemented the gradient, the Hessian properties, everything. So if you take this molecule here, which is a very popular molecule for TADF emitters for OLEDs, PTZDBT02, I just optimize and calculate the frequencies of the excited state, which I call the S1 here. And as you can see, it just takes twice the amount because it's UHF. And you can see the result, like the ring, the thiazine gets planar. It's exactly what you would expect if you had the electron transfer. And then the HOMO of the ground state is on the left side, but if you check the HOMO of the excited optimized state, you see that it's then on the right side. You do have the electron transfer and no negative frequencies, so everything works right. And you could, in principle, even calculate EPR or NMR or anything on top, because these are completely variational. There's also more information about that on the manual. This is a relatively complicated topic and I can't talk too much about it, but here is, if you have any question, please, you can always write emails. This is also my Twitter, the company Twitter. And again, thanks for your time. Thanks for being here. I hope you can have a lot of fun using ORCA 6, and that's it.